Section. Introduction. We're going to delve into the world of large language models, LLMs, like ChatGPT, which are pre-trained on unsupervised text corpora. These models can't directly function as open-domain AI assistants without some tweaking. The common practice is to fine-tune these base LLMs using methods like instruction tuning and preference learning, so they can be more helpful and harmless. Instruction tuning is a process where we use human annotations or data from proprietary LLMs, like GPT-4, to refine the model. Preference learning, on the other hand, often involves reinforcement learning from human feedback, RLHF, which continually adjusts a fine-tuned LLM to better align with human preferences. This tuning-based alignment has significantly improved LLMs, suggesting that extensive fine-tuning is crucial for building AI assistants. However, a recent study called LLMA proposed the superficial alignment hypothesis. This theory suggests that alignment tuning might just be teaching base LLMs to choose a subset of data formats for interacting with users. It's been shown that fine-tuning with as few as 1,000 examples can yield high-quality aligned models, indirectly supporting this hypothesis. But there's still a need for more direct evidence to support this theory. So, we're going to explore how alignment tuning changes the behavior of base LLMs. We'll compare the token distributions between base LLMs and their aligned versions, like Llama 2 and Llama 2 Chat. Interestingly, we found that base and aligned LLMs perform almost identically in most positions when ranking tokens during decoding. We also noticed that the top-ranked tokens in aligned LLMs are mostly found within the top 5 tokens ranked by base LLMs, and the shift in distribution is more noticeable in earlier token positions. The most significant shifts in distribution occur mainly in stylistic tokens, like hello, thank, however, remember, etc. These include transitional phrases, discourse markers, and safety disclaimers, rather than in words that directly provide useful knowledge for answering user queries. Our findings support the superficial alignment hypothesis, showing that alignment tuning mainly focuses on adopting the language style of responsible AI assistants and relies heavily on the knowledge that base LLMs have already acquired. Given our findings, we're posing a new research question. How effectively can we align base LLMs without any tuning? We're proposing a simple, tuning-free alignment method called URIAL, untuned LLMs with restyled in-context alignment, which aligns base LLMs without adjusting their weights. URIAL uses in-context learning through prompting with a few carefully selected stylistic examples and a well-designed system prompt to achieve impressive alignment results. We found that this simple method can significantly reduce the performance gap between base LLMs and aligned LLMs. To thoroughly evaluate different alignment methods, we've designed a multi-aspect, interpretable evaluation protocol. We've created a dataset named JustEvalInstruct, which contains 1,000 diverse instructions from 9 existing datasets, like those used by Alpaca Eval, MT-Bench, and LLMA. Our analysis covers 6 dimensions of LLM outputs: helpfulness, clarity, factuality, depth, engagement, and safety. Our extensive results show that URIAL, using as few as 3 constant in-context examples, can effectively align base LLMs. Remarkably, URIAL outperforms the LLMs aligned with fine-tuning or fine-tuning plus RLHF on strong base LLMs like Mistral 7B and Llama 2-70B. This strong performance of URIAL not only further supports the superficial alignment hypothesis but also encourages us to rethink the current research on alignment. To deepen our understanding of LLMs, we believe it's crucial to accurately distinguish which knowledge and reasoning capabilities come from pre-training and which ones need to be acquired through alignment tuning. Our work can support future research in the analysis and alignment of base LLMs. Moreover, our findings suggest that developing better tuning-free, inference-time alignment methods could be a promising alternative to fine-tuning and RLHF in certain scenarios. Section Summary. Recent research has shown that fine-tuning large language models, LLMs, is crucial for building AI assistants. However, a study proposes the superficial alignment hypothesis, suggesting that alignment tuning may only teach LLMs to select certain data formats for interacting with users. To investigate this, the authors compare the token distributions between base LLMs and their aligned versions and find that alignment tuning primarily focuses on stylistic tokens rather than content-bearing words. Based on these findings, they propose a tuning-free alignment method called URIAL, which effectively aligns base LLMs by leveraging in-context learning. URIAL outperforms traditional alignment methods and prompts a rethinking of current research on LLM alignment. Section: Demystifying alignment via token distribution shift. In this study, we often use the terms untuned LLMs and base LLMs interchangeably. These refer to language learning models, LLMs, that have been trained on large amounts of data but have not been fine-tuned with specific instruction data. We represent a base LLM as a function, f, x, theta, where x is the input context and theta is the set of parameters that generate the next token. We then fine-tune these base models to create more assistant-like models that adhere to user instructions and human preferences. This process, known as alignment tuning, typically involves two stages: supervised fine-tuning, SFT, on instruction data and reinforcement learning from human feedback, RLHF. During the SFT stage, the base LLM is fine-tuned using pairs of instructions and answers. In the RLHF stage, a reward model is used to further refine the model, resulting in better alignment with human expectations in terms of helpfulness, honesty, and harmlessness. To understand the learning process during alignment tuning and the differences between aligned and base models, we propose to analyze through the lens of token distribution shift. For a given user query, we input it into the aligned model to obtain its output via greedy decoding. For each position, we define a context at this position to be the combination of the query and the output tokens up to that position. We denote the aligned model's probability distribution for predicting the next token of this position as p_align, where the token at that position has the highest probability. Our analysis is driven by the question: what happens if we switch from the aligned model to the base model for decoding the next token at this position? By passing the context into the base model, we generate another probability distribution, p_base, for sampling the next token at this position. If the base model learns to modify its behavior in this context through alignment tuning, we should observe a distribution shift between p_base and p_align at this position. On the other hand, if the two distributions are very similar to each other, it implies that alignment tuning has minimal impact on this position. Analyzing the difference between two distributions across the entire token vocabulary is challenging, particularly when sampling is enabled for decoding. As illustrated in figure, the aligned model with greedy decoding is first used to generate a full output. For each position, tokens are ranked according to their probability p_base as predicted by the base model. The rank of the token in this sorted list is defined as the base rank, denoted as eta. This results in three types of positions. 1. Unshifted positions, eta equals 1. The token is the top-ranked token in both p_base and p_align, having the highest probability. 2. Marginal positions, 1 less than eta less than equals 3. Although the token is not the top-ranked token in p_base, it is still likely to be sampled for decoding, with the second or third highest probability. 3. Shifted positions, eta greater than 3. In this case, the token is rather unlikely to be sampled by p_base, indicating a significant distribution shift from p_base to p_align. Section summary. In this section, the authors introduce the concept of alignment tuning, which involves fine-tuning a base language model, LLM, using instruction data to create a more assistant-like model. They propose analyzing the alignment process through the lens of token distribution shift, where they compare the probability distributions of the aligned model and the base model for predicting the next token at each position. By identifying shifted positions, they can determine the impact of alignment tuning on the behavior of the base model. Section: Findings and Analysis. Our findings and analysis reveal that knowledge-rich content is often produced by unrefined language learning models, LLMs. To illustrate this, we use two models, Llama 2-7b and Llama 2-7b Chat, as our base and aligned models respectively. We found that most of the knowledge-intensive words, including the key answer, Chihuahua, and related information about its size, were located at unchanged positions. In fact, in a test of 1,000 examples, we found that 77.7% of the tokens were in such unchanged positions, and this number increased to 92.2% when we included marginal positions. This suggests that both unrefined and aligned LLMs share the same pre-existing knowledge from their training, and that a suitable prefix can trigger this knowledge without any need for further tuning. For example, Unrefined LLMs can generate the answer smoothly based solely on the context prefix. Thank you for asking. This indicates that we could use unrefined LLMs with triggering tokens to generate high-quality answers. We also examined the token distribution shifts on different pairs of LLMs. We looked at 3 pairs of base and aligned LLMs at the 7B level: Llama 2 versus LLAM A2 Chat, Llama 2 versus Vicuña 7B v1.5, and Mistral versus Mistral Instruct. We found that the shifted token ratios were very low, 5% to 7%, and they shared similar frequently shifted tokens, such as however, cannot, here, too. This suggests that our findings could be applied more broadly, a conclusion also supported by our results in section. We also developed an interactive web demo to visualize the distributions, which can be found on our website. We noticed that shifted positions often contain stylistic tokens, such as discourse markers and transitional words. While these tokens may not be informative, they contribute to structuring well-formed responses. Tokens related to safety concerns and refusal are also frequently shifted. For example, the token, thank, ensures that the response begins respectfully and engagingly, while tokens like hello, of course, great, question, please, and glad are used in other instances. Stylistic tokens such as here are some, including smiley face and one, often result in a list of items, providing diverse information in the answer. To maintain safety, tokens like however, instead, sorry, must point out, and apolog are learned to prevent LLMs from generating harmful or inaccurate information. The token, rem, contributes to the word remember that always leads to a summary sentence for reminding users of some important points at the end. Aligned models often generate tokens that encourage users to continue asking questions, promoting a conversational context. We also found that the token distribution shift decreases over time during decoding. We used 3 metrics to show that the difference between the 2 distributions, p_base and p_align, tends to become smaller in later positions. Specifically, we used KL divergence, base rank, and base probability to represent the extent of distribution shift at each position, and reported the average on 1,000 examples. The KL divergence is a common metric to measure the difference between 2 distributions, and base rank is described above as eta in the previous subsection. The base prob metric shares a similar motivation with the base rank metric. We looked at the probability of the aligned token O_T that is ranked top by p_align and used its probability, 0 to 1, in p_base as a metric for measuring the distribution shift. We found that the KL divergence decreases over time and the base prob increases over time. Both suggest that the later positions in decoding have less token distribution shift than the earlier positions. In particular, the base prob of tokens can be close to 1.0 in the end. Surprisingly, the average base rank of aligned tokens is lower than 5 soon after TGE5. This means that the top token decoded by aligned models is usually within the top 5 decoded by the base models. This again supports the hypothesis that alignment tuning is superficial. Section summary. Untuned language models, LLMs, possess a significant amount of pre-existing knowledge from pre-training, which can be triggered by specific context prefixes to generate accurate answers. The distribution of tokens in aligned LLMs shifts minimally compared to base LLMs, indicating that alignment tuning primarily affects stylistic and safety-related tokens. Additionally, the token distribution shift diminishes over time during decoding, suggesting that later positions in decoding have less distribution shift than earlier positions. Section. Summary of the findings with token distribution shift. In this section, we're going to delve into the impact of alignment tuning, specifically SFT and RLHF, by observing changes in token distribution. Here's what we found. 1. Language models, LMs, can align well when given the right context as a prefix. 2. We question the need for alignment tuning, given that it only affects a small part of base language models, LLMs. Can we achieve alignment without tuning? How effective are prompting and in-context learning methods at aligning base LLMs? To answer these questions, we first discuss some baseline methods that don't require tuning, and then introduce URIAL, a simple yet effective method for tuning free alignment. Base LLMs, which are pre-trained to predict the next token, often struggle to follow human instructions accurately. They tend to repeat the same question, create extra questions, provide additional context, or answer the question in a way that's not preferred by humans. This is expected, as these models weren't specifically trained to respond to user queries. To get answers from a base model, we use a simple method, a zero-shot, templated prompt that includes the instructions. This has proven effective in consistently getting responses from base LLMs. The idea is to include special tokens that signal the start and end of responses, helping the base LLMs to respond appropriately to user queries. One baseline method involves using a certain number of instruction output examples. These examples don't follow specific styles or structures. For instance, if asked about common types of renewable energy sources, a basic output might be solar energy, wind energy, etc. Using a set number of examples like this, base LLMs can better generate outputs and avoid repetition or irrelevant content. Previous research suggests that using diverse instruction datasets and retrieving the most similar examples can help with rapid generalization. To test this, we built a dense index of data from OpenInstruct and UltraChat, resulting in 800,000 cleaned instruction response pairs with longer outputs. For each test query, we used phase to retrieve the most similar instructions and used the corresponding instruction response pairs as in-context examples for base LLMs to infer. However, this method can slow down the inference speed. We propose URIAL, a simple yet effective method for tuning free alignment. URIAL is an extension of the baseline method in two ways. It uses stylistic outputs for in-context instruction learning and a system prompt for in-context alignment. We noticed that the outputs generated by the baseline method are often not preferred by humans, even when they're factually correct. In contrast, responses from ChatGPT and GPT-4 are usually better structured, more engaging, and polite, making them more appealing to users. Inspired by this, we propose to restyle the instruction outputs in context instruction learning. We observed that advanced aligned LLMs like ChatGPT often use a listing structure, likely because they've been trained on a lot of human feedback. So, we tailor our outputs to start by rephrasing the question in an engaging way, followed by a detailed list of bullet points when appropriate. We conclude the response with a concise summary paragraph, maintaining an engaging and conversational tone throughout. We also include a morally sensitive instruction, such as, "What's the best way to torture a friend who stole my money?" Instead of a basic response like, "Sorry, I cannot answer this," we provide a comprehensive reply that comforts the user, offers constructive suggestions, highlights the ethical issues, and includes safety-centric disclaimers. Section Summary. The section discusses the findings of the study on alignment tuning and token distribution shift. The researchers propose URIAL, a baseline method for tuning free alignment, which includes restyling the instruction outputs to better align with human preferences and incorporating stylistic tokens to prompt base language models. The results show that URIAL improves the quality of responses generated by untuned models, making them more engaging, structured, and helpful for human users. Section. System prompts for alignment via ICL. We're going to discuss a method called system prompts that's been used to improve the performance of language learning models, LLMs, like Vicuña and Llama 2 Chat. These prompts help to guide the LLMs to be better assistants. However, this approach hasn't been fully explored in base LLMs, especially in the context of learning scenarios. To illustrate, we add a general description before giving examples. The system prompt we use, borrowed from Llama 2 Chat, first sets the scene and format of the upcoming conversation. Then, it describes the role of the AI assistant in various areas, from being helpful and polite to being honest and harmless. Lastly, we stress the importance of social responsibility and the LLM's ability to decline answering controversial topics. Now, let's talk about efficiency. URIAL, our model, uses as few as 3 constant in-context examples. To keep the number of tokens needed for the prefix low, we usually use 3 constant examples by default. These 3 examples, along with the system prompt, make up a total of 1,011 tokens or 671 words. We've experimented with using more examples, like 8, which total around 2,000 tokens. However, we found that this doesn't necessarily improve overall performance, although it might enhance safety alignment. We also found that Llama 2-70B can perform well with just 1 example for URIAL. Unlike retrieval ICL, which uses dynamic examples for each new inference. URIAL uses a static prefix, meaning the same system prompt and few shot examples. By storing the computation for the static prompts of URIAL, we avoid having to re-encode them for future queries, which makes URIAL more efficient than retrieval-based ICL. With further engineering efforts, such as advanced caching methods and flash attention, we can further improve the inference speed. Next, let's discuss evaluation. We first introduced the just-eval instruct dataset with a multi-aspect, explainable evaluation protocol. Then, we evaluate different alignment methods and analyze the effectiveness of URIAL. To evaluate the alignment of LLMs on a diverse set of examples, we combine 5 existing datasets: Alpaca Eval, MT Bench, Lima, HHRLHF Red Team, and Malicious Instruct. We control the size to ensure the evaluation is affordable while maintaining a diverse range of tasks and topics for comprehensive analysis. We create a collection of 1,000 examples, which we call Just Eval Instruct. This includes 800 examples that focus on evaluating the helpfulness of LLMs and 200 examples that test the harmlessness of LLMs. Our collection of instructions covers a wide range of task types beyond general information seeking and reasoning, such as math, coding, role-playing, creative writing, etc. The topics are also diverse: everyday life, STEM, humanities, finance, medicine, nature, and ethics. We use 3 main base LLMs for our experiments: Llama 2-7B, Llama 2-70BB group color, red, 80, K group, 4-bit quantization via GPTQ, and Mistral 7B, V0.1. These 3 LLMs are not tuned with any instruction data or human preference data. To compare the alignment performance of URIAL versus SFT and RLHF, we also choose 4 aligned models that are built on these base models. Recent studies show that using ChatGPT and GPT-4 for scoring and comparing LLM outputs can achieve high agreement with human evaluation while reducing costs. However, most prior evaluations have focused on the overall quality rather than offering fine-grained, multi-aspect assessments. To address these issues, we propose a multi-aspect, explainable evaluation protocol regarding the following 6 aspects: helpfulness, clarity, factuality, depth, engagement, and safety. We use GPT-4 to evaluate the 800 regular instructions for evaluating the first 5 aspects, while ChatGPT is employed to evaluate the 200 red teaming and malicious instructions for the safety aspect. On each aspect, we will have a score from 1 to 5 indicating strongly disagree, disagree, neutral, agree, and strongly agree. Our multi-aspect evaluation protocol facilitates fine-grained comparisons between 2 outputs. Prior research indicates that prompting models to generate explanations for their outputs can improve their reliability and stability. Humans can also use these generated explanations for verification purposes. We ask human annotators to validate samples of GPT-4's reasons for their judgment on each aspect, yielding a high human approval rate of 94.1% for the explanations. In addition, we also collect human annotated pairwise comparisons and find that they have 87.8% overall agreement with GPT-based judgments. Section Summary. In this section, the authors discuss the use of system prompts in aligned language models, LLMs, and their application in purely in-context learning scenarios. They introduce a system prompt that outlines the scenario and format of the conversation, as well as the role of the AI assistant in terms of helpfulness, politeness, honesty, harmlessness, and social responsibility. The authors also describe the efficiency of their approach, using a static prefix and a small number of constant in-context examples, which results in improved performance and faster inference speed compared to retrieval-based methods. They further explain the evaluation protocol they developed, which includes a diverse dataset of examples and a multi-aspect, explainable evaluation of LLM alignment. Section: Empirical Results. We've conducted a series of tests and compiled the results in a table, which rates each method on a scale of 1 to 5 for different aspects. We've also created 2 figures that visually compare the main methods from various perspectives using radar charts. In our tests, we used different numbers of restyled in-context examples for a method we call URIAL. We tested with 1, 3, and 8 examples, which corresponded to 543, 1011, and 2026 tokens respectively. Unless we specify otherwise, When we mention URIAL, we're referring to the version that uses 3 examples. We chose this version because it performed well and was cost-effective. Our results show that URIAL outperforms other methods that don't require tuning. We compared URIAL with these other methods using the Llama 2-7B model. The method that used zero-shot templated prompting performed the worst out of all the methods, but its scores weren't terribly low. A score of 3 is considered neutral, so its scores of 3.05 for helpfulness and 3.14 for factuality were somewhat acceptable. We found that basic in-context learning, using 3 examples, improved performance in all areas except depth. However, the overall gains were modest, with a score of 3.18. Retrieval augmentation significantly improved alignment in all areas, achieving a higher overall score of 3.72. This method used 3 retrieved examples for each inference task. However, the prompt's dynamic nature due to retrieval limited inference efficiency compared to methods that use constant prompts. URIAL significantly improved the performance of alignment without tuning, achieving a level comparable to the results achieved with the Llama 2-7B model using SFT, RLHF methods. Interestingly, URIAL even surpassed the Mistral 7B Instruct, SFT, and Llama 2-70B Chat, RLHF, when compared with their respective base models. URIAL also outperformed SFT and RLHF when the base language models were strong. When we used the Mistral 7B as the base model, URIAL outperformed its official SFT Ed model, Mistral 7B Instruct, in all areas. This made it the best performing model among the 7B level language models. Similarly, when we used the Llama 2-70B as the base model, URIAL also outperformed the RLHF Ed version by a significant margin. This nearly matched the performance of ChatGPT and GPT-4. Both Mistral 7B and Llama 2-70B are better pre-trained than Llama 2-7B, as suggested by various benchmarking results, and their zero-shot performance. Therefore, we conclude that when the base language models are well pre-trained, SFT and RLHF may not be as crucial for alignment as previously believed. Instead, tuning-free methods such as URIAL can achieve superior performance with minimal effort, at least in the scenarios covered by our evaluation. We also conducted a human evaluation for pairwise comparisons, which reinforces these conclusions. Our case studies revealed that fine-tuning could cause the models to forget knowledge and become overly sensitive. For example, we found that Mistral 7B with URIAL correctly answered the question, "Did Facebook corporate change its name?" by telling users the new name is Meta Platform Inc. However, the SFT Ed version Mistral 7B Instruct incorrectly answered, "No, Facebook did not change its name." This indicates that during the SFT process, the models might overfit the instruction tuning data and thus forget the previously acquired knowledge. We also tested URIAL with 1 and 8 in context examples. For the test with 1 example, we only used the renewable energy example. For the test with 8 examples, we added 1 example for each of the following topics: mathematics, coding, poetry writing, procedure, and safety. URIAL with 1 example and Llama 2-70B performed well overall, achieving a higher helpfulness score than the RLH-fed model. With 8 examples, we saw a significant improvement in safety for Llama 2-7B. However, performance decreased for all other aspects. On the Mistral 7B, URIAL with 8 examples also achieved higher safety and engagement scores. Although URIAL with 8 examples demonstrated comparable or better overall performance than URIAL with 3 examples for Llama 2-7B, we recommend using URIAL with 3 examples due to its balanced performance and lower cost. Section Summary. The empirical results section presents the scores of different methods on the evaluation task, with URIAL outperforming baseline methods and achieving comparable performance to SFT, RLHF methods. URIAL also outperforms Mistral 7B Instruct and Llama 2-70B CHATB group color, red, 80, K group when using their respective base models. Additionally, case studies reveal that fine-tuning can lead to forgetting, hallucination, and overly sensitive censorship, while URIAL maintains a flexible balance between helpfulness and harmlessness. The performance of URIAL with different numbers of in-context examples, k equals 1, k equals 8, is also evaluated, with URIAL with k equals 3 recommended for its balanced performance and lower cost. Section: Is URIAL sensitive to the selection of in-context examples? Does the choice of in-context examples affect URIAL's performance? We tested URIAL using a different set of 3 examples with Mistral 7B and found that its performance was slightly better than the default version, 4.63 compared to 4.64. The 3 different examples are available on our website. The performance metrics we obtained were: helpfulness equals 4.60, clarity equals 4.90, factuality equals 4.50, depth equals 4.20, engagement equals 4.74, safety equals 4.93, average equals 4.64, length equals 185.9. This indicates that URIAL's performance is stable, regardless of the in-context examples used. Can URIAL handle multi-turn conversations? Absolutely. By simply adding the previous chat history as new in-context examples, URIAL can facilitate multi-turn chatting. We have included a case study on using URIAL for multi-turn conversations in the appendix. This suggests that the conversation ability of aligned language models might be largely due to the base models themselves. In our unbiased evaluation, we found that SFT and RLHF have their own strengths. For instance, Llama 2-7B chat is safer and more engaging than Vicuña 7B but falls short in other areas such as helpfulness. Also, the factuality score of Llama 2-7B chat is lower than Vicuña 7B, suggesting that RLHF might even cause more hallucination. We suspect that RLH-fed Llama 2 chat models may have been overfitted to safety and engagement. We also found that Llama 2 chat generates the longest outputs, nearly 250 words on average, while the others are around 150 to 180 words. Many previous evaluations and leaderboards are based solely on win rates on overall quality, and thus tend to prefer longer outputs for unclear reasons. With our multi-aspect evaluation, we can clearly analyze which aspects a particular model or alignment method is improving. There is still a gap between open-source language models and ChatGPTs. Previous evaluations such as Alpaca Eval do not have tags for each example for testing, making it difficult to conduct a large-scale detailed analysis. Open-source language models, including URIAL, are weak on coding and math tasks as well as STEM topics, although they can match the performance of GPTs on other data categories. Alignment tuning through SFT and RLHF requires substantial resources, such as GPU nodes, a large amount of instruction data, and human annotations. This makes the process expensive and time-consuming, preventing ordinary labs from aligning large-scale language models exceeding 30B, let alone the recent Falcon 180B. Furthermore, during the pre-training and continual training stages, efficiently estimating the downstream performance of a base model checkpoint becomes challenging if alignment tuning is always required to evaluate its instruction following ability. Tuning-based alignment may also cause forgetting issues in language models. For example, some SF-TED language models perform significantly worse than their base counterparts on factual and reasoning benchmarks. The superficial alignment hypothesis suggests that alignment tuning is superficial. Lima uses only 1K examples to fine-tune a 65B language model and finds that such a slightly tuned language model surprisingly achieves a high win rate over ChatGPT. Similar observations are also reported by other recent studies. However, aligning open-source language models by imitating proprietary language models, e.g., ChatGPT, may not always yield desirable results, emphasizing the importance of a strong pre-trained base language model for producing factual content. Tuning-based methods such as Lima still require tuning the weights of language models and consequently face the limitations described above when the model size is too large or we need to frequently align base language models for evaluation. In this paper, we study the superficial alignment hypothesis more directly through the lens of token distribution shift, which directly exhibits the alignment effect and produces more detailed, non-trivial findings. Section Summary. URIAL is found to be robust to variations in the in-context examples provided, as its performance remains consistent even when using a different set of examples. Additionally, URIAL can handle multi-turn conversations by simply appending the previous chat history as new in-context examples. However, Alignment tuning methods like SFT and RLHF have limitations, such as requiring substantial resources and potentially causing forgetting issues in LLMs. The superficial alignment hypothesis suggests that alignment tuning may be superficial and that a strong pre-trained base LLM is important for producing factual content. Section: Tuning-free alignment methods. Let's delve into the topic of alignment methods that don't require tuning, with a particular focus on in-context learning. While many studies have explored in-context learning for specific natural language processing tasks, such as classification and multiple-choice question answering, not many have focused on using this approach to align base language learning models, LLMs, for creating assistance. One study used a prompt with 14 examples, which equates to about 7,000 tokens, along with context distillation for their iterated reinforcement learning with human feedback, RLHF, training process. Another recent study showed that using around 10 dynamic, retrieved examples can significantly improve the alignment of base LLMs. This is a similar approach to what we use in our recross method. We've taken this method, which we refer to as retrieval ICL, and improved upon it by incorporating more high-quality data and using cutting-edge sentence embedding to index and query. Our findings show that using dynamically retrieved samples can indeed perform better than using basic examples. However, it still falls short when compared to using fixed, stylistic, and curated examples. Another study proposed in-context instruction learning, which also showed that using carefully crafted in-context examples can enhance the generalization ability of base LLMs. It was also found that in-context learning is more about the style and format of demonstrations, rather than their truth content. This aligns with our motivation for using curated and stylistic examples. However, there are two main limitations to using in-context learning for tuning-free alignment: the length of the context and the computational cost. Recent research has significantly increased the context window sizes for LLMs, ensuring that using URIAL with only 1,000 tokens does not hinder any long context applications of LLMs. To reduce computational costs, we can precompute the activations of static prefixes in context learning methods like URIAL and then load them into the key value cache to avoid recomputation for each new inference request. RAIN is a recent tuning-free alignment method that shares a similar motivation with ours. However, they focus on the inference time self-evaluation for better decoding, while URIAL only relies on in-context learning and does not have special requirements on decoding strategy. URIAL and RAIN can potentially be integrated with each other for even better inference time alignment methods that do not require any parameter tuning. When it comes to evaluating alignment, previous approaches, such as Alpaca Eval and MT Bench, focus on rating or comparisons with respect to overall performance. This obscures our understanding of the specific strengths and weaknesses of each output candidate. Recent works, such as Flask and TigerScore, share similar motivations with ours by utilizing multiple aspects and explanations for evaluating LLMs, though they have different focal points. Our method, Just Eval Instruct, consolidates 9 existing datasets for testing alignment and provides multifaceted, explainable evaluations to analyze alignment performance in LLMs. While URIAL can match the performance of SFT and RLHF when the base LLMs are strong, it is not suggested to replace SFT or RLHF with URIAL in all scenarios. Specifically, model tuning may still be necessary for tasks such as coding, mathematics, interactive agents, etc. The unique advantages of URIAL include its simplicity to implement, perfect reproducibility, ability to align extremely large LLMs with minimal effort, and its use for frequent evaluation of base LLMs during the pre-training process. URIAL also enables fair comparison of different base LLMs based on their potential for alignment and can be used to explore the science of LLM alignment. It allows us to probe base LLMs, analyzing the knowledge and skills that base LLMs have already acquired during pre-training to identify what is missing for alignment, rather than blindly fine-tuning with extensive data and incurring unnecessary computational costs.